I recently put a poll on what do you want the next episode to be, and 100% of the respondents said they wanted to know what I think about AI. Well, it's complicated. I'm going to approach this through a few obvious questions, and there'll be chapter markers for those major questions. And we'll start with the big one, which is, will ChatGPT and so forth take my job? Presuming you're a normal person, not some kind of giant nerd like me, you probably really first heard of AI in the last few years because of chatbots and the underlying technology LLMs, which stands for large language models. If you've got access to one of these LLM chatbots, what I'd like to suggest you do, pause this video and ask it a few questions about a subject where you are an expert. Welcome back. When I did this experiment, I found that the answers were always written in a way that conveyed high confidence. Some of the answers were correct or very close to correct, and some of them were wildly wrong. Since I first did this, I've assumed that whenever I ask it about something that I don't already know the answer to, the LLM and the chatbot are going to be at least as wrong as they were when I asked them about something I did already know. Now, your experience may have been different. You might have asked it about things that you already know and it happens to already know them, in which case that's not a great illustration of things. But when I asked a variety of large language models about an aspect of UK culture that I'm quite familiar with, 3 of them got it right and 1 of them didn't know anything about it. It's really dependent on the LLM that's backing the answer. It's dependent on what it was trained on. It's dependent on how it was trained after the vast corpus of text that it ingested. It's dependent on how it was quantized and a variety of other technical things. So some of them will have very robust knowledge on certain topics. Some of them will appear to have very robust knowledge on all topics, but all of them will always sound confident. And I can guarantee that none of them have full expertise on all subjects. So their confidence will always be somewhat prone to being misplaced. We know that they're not going to be totally accurate, but let's go on to whether a chatbot or the underlying LLM can do your job or my job. The first thing to say there is that none of the current generation of AIs can actually move things in the real world. So if your job involves moving stuff around, you're safe. The other aspect where LLMs can't safely be used at the moment is if your role means you interact with people. Part of your responsibility is to make commitments on behalf of your business. So if you're customer facing and you have to, agree whether or not the customer can have a refund or whether or not they can exchange an item or process their order update requests in any way that allows you to commit the business to a certain course of action, then you can't be safely replaced with an LLM. And that's because of what is euphemistically called prompt injection, which is where the person who's interacting with an LLM can make it say whatever they want. And there's architecturally, with the way how LLMs fundamentally work, it's very, very, very difficult to see how this problem can be structurally addressed. I don't like the name prompt injection because it is named that to sound like SQL injection. And in terms of how it works, there is a great similarity there. So it's a good analogy in that respect, but the comparison falls down because SQL injection was always a programming error in the client code. It was always a mistake that someone had made and they didn't have to do it. Whereas prompt injection happens because of how the large language models fundamentally work, and it's not going to be able to be fixed by just changing how the chatbot front end works. It has to be fixed in the LLM infrastructure, and it really isn't clear at all that it can be fixed without completely different architecture, in which case we're not dealing with LLMs as we currently know them. We're dealing with some other kind of artificial intelligence that does not yet exist. For that reason, I say your job is not at immediate risk of being replaced by AI if you can commit the business to courses of action, because it just can't be trusted, and you can. But what about jobs which don't involve physically moving stuff and don't involve interacting with external customers and suppliers? The software engineering work I did doesn't meet either of those criteria, so we should look at whether a large language model can replace that job function. And I'll start by saying that I certainly think a large language model could score really well in a job interview for the kind of work I did. Doubly so if the interviewer is not themselves an engineer, because when a non-engineer is interviewing a software engineer, or non-software engineer is interviewing a software engineer, all they can scan for in the technical details is confidence. They can't check competence directly because they themselves don't know how a software engineer should be answering this question. And a large language model always sounds confident and plausible. And so it would interview really well. I will say also I've used some large language models designed to be good at software programming, and they are really, really very good at the kind of questions that people typically ask in software engineering interviews. Now, whether those questions are themselves actually helpful is debatable, but I would expect to lose out in a who can leak code best competition against Microsoft's 5.4 model or against QWen Coder. Let's move on to, could it do the actual job? The valuable parts of the job that I used to do, and by valuable I mean why a business would pay me to do it rather than a cheaper person, those were helping management to draft policies to achieve their objectives. So when you as business managers want your code base reshaped in a certain way, or you want your engineering teams to behave in a certain way to avoid a certain problem that you've identified, that is one of the areas where I would be valuable. And the reason I can be valuable there is I've had 25 years of experience of how software development teams behave in response to being asked to do things in various different ways. If you want to change how they behave, I know what levers you can pull to get certain effects. Now, it's very likely that the objective that you have in mind is subtly different, or not going to be exactly the same as any of those changes we've tried to make in the past, but it's really a psychological, group psychology of a specific group of people that I've, as it were, been studying question. And I suspect that unless the large language model that you're using has been specifically trained with human feedback from people who've had my kind of job experience, which is certainly something you can do, but unless that has happened, there's not enough written down in training data that a large language model would have been trained on that is going to have trained a general large language model to do that job. However, once we know what it is we're trying to do and the lever we want to pull to do it, a large language model could be a great accelerator here in the cause of getting it done, because they can help very much with communication clarity. Once you know a way to say what you want to say, you can have them redraft it into more direct language, into the more active voice, into simpler language, into any kind of style that you particularly want, because they're built as transformer models. Those are designed to do translation, and really what you're asking them to do there is translate English to English, but change the style. They are super good for that. For that particular piece of what I used to be called on to do, can an LLM actually do it? Not in general as it sits, they can't do that. Can they make it faster, more efficient, more effective? Yeah, I think they can. Another area where I've added significant value to businesses is when the business leadership has an idea, they want to build some technology to do this thing. And my role was often to sit with the management or business leader who wishes to do that and help them by asking them questions and using my knowledge of what is technically feasible to develop that initial thought into something that can be done and that does have the effect they actually want much more specifically, so that we could measure whether the system as built did indeed solve the problem that they wished it to solve. I've tried a few LLMs and chatbots, and again, out of the box, none of them could do this because they are designed to respond to questions that I've asked in as helpful a way as possible, but never to question the user's judgment and never to question whether that idea is in fact going to fly or just fundamentally can't be done. They very, very, very reluctant to ever tell you no, and they will also almost never ask clarifying questions. I have not fully tested this, but I've had some success in getting an LLM to be able to do this part of my job by changing its system prompt. System prompt, if you don't know, is a hidden part of a chatbot which tells the chatbot what it is and how it's going to behave, or how it should behave. And so you could write in the system prompt something like, you're an assistant to the user, your job is to ask the user clarifying questions to help them develop the ideas that they have and to make sure that they have clarity of purpose within themselves. You should identify the largest amount of vagueness in their idea and ask a question that causes them to think about it. If you put that in the system prompt, you can get some interesting results. I don't know whether it would be able to fully replace a proper software engineer, because when I'm having a conversation with you about what's technically feasible, that's taking into consideration the resources that the business has, the policies that the business has that we are not in a position to change ourselves, and other pieces of business context that the LLM will not know unless it has been retrained to know those things. And that's expensive to do. You can, of course, type all that context into the system prompt as well. But what you'll run into as a problem there is that all of that information and the instructions on how to behave will use up almost all of the context window that the LLM has. You might get one or two questions into your conversation, and then it will have started to forget those parts of the context that you previously gave it that have dropped out of its short-term memory. It is probably possible to get a large language model or a system derived from one to do this job entirely. As it stands, I don't think it's particularly practical to do so unless you're willing to retrain a LLM with reinforcement learning on human feedback to know all of the stuff about your business context that an engineer in your organization normally has. The next area where I added value is once we have a requirement for something to do and it's technically feasible and business has decided to do it, it was part of my job to convert that into units of work that software development teams can do. I think this is probably beyond the reach of large language models to do the dividing up, because there's no reason that a large language model should be able to conceptualize how to divide a chunk of work most reasonably. It's a job for a different kind of AI model if you're going to use an AI model at all. However, again, similar to the first part of my job, once you have a way to badly write down what you want each team to do, the LLM can write that out nicely in whatever style you want, much more effectively and rapidly than a normal human can do it. Again, it's in the category of I don't think it can do it now. I'm fairly sure it actually won't be able to do it ever, but I'm not saying no AI can ever do this, but I don't think an LLM is the way to do this, but it could certainly make the process faster and smoother. The next stage of my job would be negotiating the timescales for the work to be done between the business leader and the software development teams, making sure that no one's asking for an unreasonably long time to do a task, which requires me to know how long it should take, and also making sure the business isn't asking for it to be done unreasonably quickly, which again requires me knowing what a reasonable time for that task to take is, and then monitoring the progress of the project, making sure it's being done to the standards we agreed to, yada, yada, yada. There's no basis for thinking that an LLM would have any way to model how long a specified software engineering task should take to do. It's not reasonable to think that it would have learned those concepts from its training data. And if you wanted an AI to know those things, you would not start from an LLM again. I don't think an LLM can do that job, but again, a lot of this process is communications and relaying in the language understood by software development teams what the business wants, and relaying to the business in terms that they understand where the software development process of that thing is at. So we're back at, realistically, we're doing English to English translation. And again, that's what transformer models and LLMs are really very, very good at. And finally, from time to time, I would write some code, but really not all all that often. I would spend a lot more time reviewing code and doing the other things I've talked about. I have tried using an LLM to write code. I personally think that I can write better code than it can, but I certainly can't write code at the speed that it can write code. And I would suspect that the majority of businesses would be better served by having, 90% as good as I could write it code written 1,000 times faster. That's the value proposition of having an LLM write code, and it's for a lot of use cases, it's quite hard to argue with. Sometimes what you're trying to do needs to be done absolutely correctly first time, and that's where you should be paying someone like me to do it. And sometimes you're just trying to mess around, experiment with stuff, see what feels like it's going to work and what doesn't. And for that, you're going to make progress hundreds of times faster if you are using AI to write your code rather than waiting for humans with keyboards. Of course, even better is humans checking that what the AI has written makes some kind of sense. If you're just using AI, you're probably a bit mad at the moment, but it has improved in its ability to write code a lot over the last few years. Anyway, that's my summary of could a LLM do the job that I'm no longer doing. And right now, an LLM can't do all of my old job, but it can do some significant parts of it. It can be used to improve the quality or speed of execution on most or all of the other parts of the job I used to do. As economists would say, that means the productivity of a software engineer should increase by using AI to augment what they're doing. The original question is AI going to take your job? And that's a pretty complicated question of economics. It's going to have a lot of effects on the productivity of a lot of job roles. If we assume what I've just said is fairly accurate, it will be a big increase in the productivity of software engineers. So if nothing else changed, that would mean that there will be fewer roles for software engineers. But there's other scenarios, right? There's the absolute disaster for the profession scenario of the places where I identified that an LLM probably can't do it. Well, someone could come up with an AI model that can do those things, and then there's no role for software engineering at all. That's certainly a possibility. The optimist's case for AI's effect, though, is that if the business side also gets a productivity boost that's larger than what we get in the engineering layer, and it's also possible that software engineering teams who get their technical direction from us will see a larger productivity boost than we do. That means that the demand for software engineering service, which is really this bridge role between programmers and management, demand for that could go up by more than the amount of the efficiency increase, meaning that there'll be many more software engineering roles than there currently are. And AI is not taking that job. It has just made it pay more. I really cannot say where on the spectrum reality is going to be. Perhaps it will, net out to making no difference because everyone's productivity will shift roughly the same amount. If I were still doing a software engineering job, I would want to be using large language models already to increase my productivity, because if there is going to be a squeeze on software engineers, as in general the productivity of them increases, you want to be the one with the highest productivity because you'll be squeezed out later in the game that way. While I'm skeptical about the wisdom of using, subscription cloud-based chatbot things, I think there shouldn't be any safety or privacy concerns with using locally run large language models. And so that's what I would be suggesting that you do if you are still in a software engineering role. I want to make one personal observation on the subject of chatbots in particular. Chatbots of various kinds have existed for many decades, and in the past I had extensive exposure to chatbots before large language models were even a thing. I found then, and I suspect it's still true now, that how I speak and behave when interacting with the chatbot starts to leak into how I speak and behave when interacting with real people. Back in the day, I made a conscious effort to avoid anthropomorphizing the chatbot and to write to it as though it were a mere device, because obviously that's what it is. But the problem is that the human brain is a learning machine. Whether a chatbot can pass the Turing test or not for a consciously thinking human turns out to be irrelevant. If you're talking to something in the way that you talk to humans, your brain will learn that that's how you should talk to humans, whether the other end is a human or not. I had to treat the chatbots in the way that I wanted to be reinforced for when I was speaking to humans. So I have to say please and thank you to the chatbots in order that I still treat humans courteously. You may or may not find that you have the same problem, but I'm putting this anecdote in here in case it does affect you in the same way, because it's a pretty easy fix. And I think it is worth watching out for. So there's obviously a lot more to deep learning than large language models, and we should talk about some other ways you could use it. So I have a couple of mathematical problems that interested me at the point I started doing the research for this. I decided, okay, look, I'll just get a load of data together, build a deep learning neural network, chuck the training data in, mix it around a bit and see what happens. I'm by no means an expert. I haven't built very many AI models in my lifetime, and I have only, I would say, the beginnings of an intuition about how everything works. What I found so far has been quite interesting, and there's good pieces and bad pieces, so we'll talk about all of that. The more neurons you've got and the layout that you give it, it defines how much freedom the neural network has. If you don't have enough freedom, then the model will be unable to find a good approximation to what you're trying to teach it. If you give it too much freedom, then the model is going to prefer to memorize exact answers for the training data. And that will mean that the result when you give it any other input is going to be the wrong answer. There are techniques to prevent it memorizing the input, the training data, and I have tried using those with a certain amount of success, but actually in neither of the problems I was using did I find it necessary to do that. For one of my problems, I had 2.5 million training data points, and the training data was perfectly accurate for the function I was trying to model, and it was also normalized, which I'll talk further about a bit later. Normalized inputs, normalized outputs. No neural network architecture that I tried, and I tried a bunch, could get anywhere towards converging on an answer for that particular function. It means that there's some hidden prerequisite. So as well as having a lot of training data, I should clarify what we mean by that, generally speaking, is inputs and the corresponding expected outputs of the function. In this case, there's other ways of doing it, which are inputs and some way to score how good the output of the function of the approximation is. That's fundamentally what you need. But in the cases I was training for here, it is a piece of code that does some maths that I'm trying to approximate, of basically to find a fast way of doing something I already know how to do. And as I say, in some cases, you can feed that into a neural network and it just cannot find a way to get to the right answer that you're looking for. One annoying thing about the way the deep learning networks work is actually I can't even say that what I've just said is probably true, but I can't confirm it. Because what I know is that after quite a lot of trying, I did not find a network architecture and training regime that was capable of converging for that problem. Doesn't mean that it doesn't exist. The next person to come along might try something different and it might work. It's an important part of the engineering consideration when you're thinking, oh, I should use this with AI. All you can ever say is, I should try to solve this problem with a neural network. And you have to accept that sometimes you will not be able to do so. There are problems which an AI cannot efficiently solve, even though you have what seems like it should be sufficient training data. And it may be that there are problems which cannot be solved, even if you have a complete set of training data, like every possible answer. Doesn't mean that there will be a neural network that can do that approximation that is smaller than all of the training data. And equally, just because you haven't found it doesn't mean it is unsolvable. It's a bit too trial and error at the moment. I did look for, and I could not find a general way of how can I know if this is going to work, and how can I know what shape of neural network I should use. That doesn't seem to exist for general problems you're looking at. However, the second problem that I tried to approximate with deep learning model, I could get it to converge, and I have some observations from that. I'll describe what I was trying to do. I have a launch monitor for golf, which is a piece of equipment that already exists, and it measures the initial linear and angular velocity of the golf ball after I hit it. And then as it's currently constituted, it sends that information to a application that runs on a PC or on a tablet or something, and then that does some graphics and whatever and tells you where the ball would have landed had you hit it in still air on over flat ground, which is a fun load of data that golfers are very interested in for various reasons. I don't want to lug a PC around with me. I don't want to have to deal with the tablet on a tripod thing. I want to build an embedded system that has a small microcontroller, connects to the launch monitor over its USB interface, and has a tiny little LCD screen which puts the numbers I want out of the system on the LCD after I hit the ball. Now, I've got the code to do all the physics calculations required to work out the ball's flight and where it lands and get the numbers that are interesting to golfers out of that. And there's about 5 numbers that we all care about. And running that piece of code, if I do it on a recent desktop CPU, takes about 15 milliseconds, but it's all floating point calculations, and that's on a desktop CPU which runs at 4 gigahertz or so and has about 80 watts to spend on doing the task. I need to be able to calculate it on a embedded CPU, and an embedded CPU runs about 40 times slower for integer calculations, and it doesn't have any capacity to do floating point maths, so that has to be emulated if you really need to do it. That means that if I were to run the same calculation on the embedded CPU, it would take about 2,000 times as long as it does on the desktop, which is about 30 seconds to produce the answers, which is too slow to be a viable option for this case. I could get a fancier CPU to run in this system that does have floating point unit, and that would then allow it to run in maybe 200 milliseconds, which would be fine. But such a system has a lot of implications for packaging. I'd need more power to run it. I would probably need active cooling, so I'd need fans and vents, which means the system wouldn't be waterproof without a bunch of work. There's a lot of knock-on effects to just using a more capable processor, is what I'm trying to say. So I thought it would be at least worth the effort to see if a deep learning model could learn how to do those calculations. Then we can assess whether it can then be more viable on the microcontroller than doing the actual maths. I was successful in training a deep learning model to approximate the calculations. I, in fact, trained many such models to find a good one, but a representative one of those takes around 20 microseconds to evaluate the model for a launch on a desktop CPU. So that is about 1,000 times faster than the numerical integration. That brings it down to 30 to 40 milliseconds for the microcontroller to do the calculation via AI. And that is totally acceptable, whereas 30 to 40 seconds are totally unacceptable. This does seem possibly, and we'll come on to the caveats in a little while, it does seem like it could possibly be a solution to my problem. I spent a considerable amount of time training different models on this problem to see how good I could get it. I initially had nothing converging at all. I quickly realized I needed to do input normalization to get the model to do anything useful. And just doing that with a few layers was getting the model to converge. It was getting more accurate for many iterations of training and then reaching a plateau, which is what you expect to see. But when I evaluated those models for their accuracy, they were really very, very bad. I'd asked all of the LLMs that I have access to for a sort of template architecture for I'm trying to approximate a piece of numerical integration code in a AI model. What kind of architecture should I do? What do I need to have for training data and all of that? And only one of them said I needed to do input normalization, and none of them had suggested I would need to do output normalization to get the results to converge. When I added output normalization, I got transformatively better accuracy of the of the converged model. With the original model, the best I could get it to converge, it was so bad that you would say I'd rather wait 30 seconds for the actual answer than accept this. As soon as I added output normalization as well, the training convergence improved massively to where it gets things within 5 yards of perfect 95% of the time, which is probably okay. It's within 7 yards of perfect 99% of the time. And that's probably still close enough for me to use those numbers if I had to stick with them. That was actually the result of the first model where I added output normalization. The way this actually works is I train a model with normalized outputs, and then I manually add on a output denormalization layer to the top of on top of that model, so that as far as the final thing that's produced is taking denormalized inputs, then the first layer normalizes them, then it goes to the model, and then the last layer denormalizes them. And thus I get the training stability that comes with using normalized data for the training, and I get the model still is mapping from the nums I have to the nums I want without having an external normalization or denormalization step. As I say, I got results that were probably acceptable, but I shouldn't accept them because it's just this is the first one that's really worked at all. I haven't done any tweaking to the architecture or the training regime to see if I can improve it. The first model, as I say, gets the exact right carry distance 35% of the time, and it gets it within 7 yards 99% of the time, and it's within 3 yards about 90% of the time. I just added a couple more hidden layers to the same model. So the initial model had 2 hidden layers. I just added 2 more, and that makes the model twice the size. It makes it half the speed to evaluate on the microcontroller. But if the accuracy gain is worth it, you might take that trade-off. And so that one is within 4 yards 99% of the time. It's within 1 yard more than 80% of the time. And it's spot on more than half the time. So that's pretty good. I tried adding some more layers to that, and it got worse because the training mechanism causes it to start memorizing the actual answers for some of the input parameters, and that means when you go to validate it against other numbers, its performance is terrible. I then thought, hold on, there's a lot of trigonometry in the actual physics calculations, and I haven't given the AI model here any way of doing any kind of trigonometry function. I was using the ReLU activation function, which is basically it sets things to 0 if they're less than 0, and otherwise it uses the actual value. So it's pretty much a linear transformation. There's not a way to do any kind of angular calculation with that particularly, or it's not super obvious, or at least you're going to need to use a few neurons to do it rather than being able to do it in one neuron. There's another activation function, or in fact a bunch more activation functions you can use on neurons, and I switched some of the layers to tan H, which is, as it suggests, it's got quite a lot of trigonometric basis to it. So I thought, well, if I give the neural net or some layers of the neural network access to that trig functionality, it might help it converge faster on a good answer. And yeah, it works. So that model is within like 2.5 yards 99% of the time. It's spot on 72% of the time, 72%, and it's well over 90% of the time is within 1 yard. I'd be very happy to kind of rely on those. That's certainly accurate enough. However, we're still there on a 4-layer model, and we've now got some trig functionality in there to evaluate it. So we've made the model larger and slower than we perhaps would like it to be. And the quality is great, but I would accept slightly lower quality in exchange for it running faster and being a smaller amount of data, because I'm limited in the amount of data I can store on a microcontroller, as much as I'm also limited in how much runtime I want to allocate to this thing. So the 4th model that's interesting is similar in size to the first one. So I think it's back to 2 layers. All of the layers use the tan-H activation function, but its performance is between the 2nd and the 3rd model. overall. So it hits 99% accuracy at around 3.5 yards. Noticeably, but not hugely worse than the third model, but it's half the size, as I say, and that means it's twice as fast to do the calculations. I don't know if any of these are actually going to be usable for me on the kind of microcontroller I normally would use, because I don't know if it will fit, if any of them will fit in the size budget that I've got when I add in the supporting code that's needed. If either of the TAN-H type models do fit in and they perform well enough, then I think my problem's solved. If they don't fit in, then I'm back into asking myself, which problem do I want to have? Do I want to have to add extra memory and extra stable storage to this small microcontroller? Do I want to try and make these models smaller using quantization or integer maths? Or do I want to go up to, again, a larger microcontroller that has more suitable features out of the box? But if I do that, am I still wanting to stick with the AI model, or is it cheaper to jump to the case where I can just do the actual perfect maths fast enough? As I say, I haven't yet evaluated the answer to that question, but I'm just relaying that to give you a sense of how this kind of engineering decision, whether or not to use AI, isn't particularly always straightforward. The other thing I do want to talk about is I've told you about 4 of the models that performed quite well and were a sort of promising line of inquiry. I must have trained hundreds of others with variations on the architectures that either performed similarly or worse or failed entirely. And I found the process quite annoying to go through. There's a huge number of ways, possibly infinite number of, well, there are an infinite number of ways you can always add layers, but there's a huge number of ways to vary what each layer's setup is. And I have not yet acquired any particular intuition for if any such change is going to be helpful to me, harmful to my model's architecture, or is going to in fact do nothing. As an engineering process, if you are setting off trying to train an AI model to approximate some function, you have to hope you're going to be able to find a model that's good enough. And if you do find a model that's good enough, you're going to probably want to some extent optimize it. But you've got to accept, I think, the game isn't that you're going to stop when it's optimal. You're going to stop when you get bored of trying further things, and you're going to take the one you found that was best to that point. I realize there are lots of other ways I could have addressed this problem with deep learning. I've looked for a model that approximates the whole calculation in one go. I could have tried to find a deep learning model that does slices of that physics, a small part of that physics calculation, like a second's worth of it rather than the full ball flight or 100 milliseconds worth of it. And it's possible that I might find a really accurate and smaller model that can do that. And then I could iterate it over and over to get to the answer that I'm actually looking for. So I'm sort of doing the numerical integration, but replacing the innards of the numerical integration loop with an AI model that just does that internal part. Almost infinite number of ways of slicing this, and there's almost infinite ways of designing the neural net for any particular way of slicing it. It's there's a lot of freedom, which is good if that's what you want, but there's not a lot of signposts, which is bad if that's what you want. The other thing with this is everything I've talked about so far has been, I've given you numbers for performance on a CPU. You're probably aware that most neural networks popularly get run on GPUs, and perhaps you're wondering how much difference that makes. Well, if I have a single golf ball launch and I send it to my GPU, it takes 11 microseconds to run the AI model, which is a little bit faster than the 15 microseconds it takes on my CPU, but it's not transformatively faster. But that's for a single question, single answer. And while it's doing that processing, it needs 115 watts of power to do it. It's really stupid to send one at a time to the GPU and get the result back because of how expensive it is in power and how very small the speed up is compared to just doing the calculation on the CPU. So you shouldn't do that if that's the nature of your problem. And so for my microcontroller type example, I wouldn't want to have to embed a GPU in there because I wouldn't want to supply 115 watts to something that would just mean your battery life is 3 seconds maybe. Where the GPU really comes into its own is if you send a big batch of launch information to the GPU, like a lot of different launches, and ask for all of the answers at once. I sent it 1 million launches, which is my entire training and validation dataset. That took 65 milliseconds for the whole lot. So 65 nanoseconds for each question, which is incredibly fast when amortized. The next question I want to answer is, should you buy one of these AI-enabled or AI-capable PCs? That's really a choice for you. My PC already meets the requirements of the Microsoft Copilot Plus program because I have a NVIDIA 3090 in this machine. That means I can use large language models locally on my computer and get results really quickly from them. That particular certification program requires a certain amount of what they call AI tops. My machine here has about twice the amount that's required to meet that standard. It produces stuff from the LLM way faster than I can possibly read it. So I would say that if you have half of that compute capacity and enough memory attached to that compute capacity to run a local large language model, you're going to be pretty satisfied with the results. I will also say I own a laptop which does not meet the requirements. I can run large language models on it, but it is excruciatingly slow to the point where I just don't bother. And it's roughly the same for other kinds of AI, such as image creation, that kind of thing. Locally on my laptop are very bad. Locally on my machine with a proper GPU, really very good. The other thing to be aware of with the Copilot Plus certification, that requires only a specific kind of AI compute, which is going to give you quite a good experience if you're using a LLM that's already trained. If the system only has that kind of coprocessor in it, then it won't be suitable for training your own large language model locally. Think about your use case. If you do want to do your own training and you've got the budget for it, you're going to want something with a high-end NVIDIA graphics card as things stand. If you're just wanting to use the models for what someone else has already trained them to do, then you've got a much broader range of things you can pick from, and in particular the AMD Ryzen AI Max systems look like they could be pretty special because they have vast amounts of memory available to access from the AI coprocessor, which means they can run very large models. Occasionally get asked by people if they should invest in any of these companies, particularly NVIDIA, and in real life and on here. I won't answer that question, but I do think there are some things you should consider before you put your money anywhere, and that's just in the spirit of, if you're placing a bet, you should know what you're betting on, basically. With particular reference to should you invest in NVIDIA, who are the undisputed market leader in the GPUs that people are currently using to train almost all AI models. The current wave of neural net architectures are reliant on being able to do a huge amount of what we in this software engineering trade call embarrassingly parallel linear algebra. But it's worth digging into why that is. The reason, so far as I've been able to determine it, is because the existence of GPUs made it possible to do huge amounts of embarrassingly parallel linear algebra. That supply existing meant that models that rely on that had a relative advantage over other kinds of models that they did not previously have. It's supply of that kind of thing driven to an extent. Now, because, well, that is all that exists at the current large scales, and because it's been the focus for the last 10 years, there's a lot of people in the industry for whom that's the only kind of AI they've ever encountered. There's a large incumbency effect that means it's probably going to be around for a relatively long time. Let's say at least 5 years it will be the dominant AI architecture. But the thing you need to consider before you put a bet on their success is there's a possibility that someone already has a better architecture, like fundamental architecture, than this parallelized linear algebra. It's possible that they can design a different kind of chip that makes that architecture viable. It's possible that's already in production and we don't know about it. It's not outside the realms of possibility that in a few years, this linear algebra based round of AI is regarded as an interesting footnote on the path to efficient AI models that are considerably more intelligent. Remaining on the subject of whether you should or should not bet on a GPU design organization, particularly if you're from the AI boomer side of things, consider that if you're betting on a GPU designer, you're betting against the near-term development of any kind of human level or better AI model. Because if someone has an AI model that's human level or better, the first thing, or one of the first things they should ask it to work on is to design a maximally efficient and or maximally performant chips to run itself on, because the NVIDIA chips are designed by humans. If you have a human level AI, an AI that can do anything human can, you can have it design those chips for you. And then you can go straight to a chip manufacturer like TSMC to have them made. And obviously, I shouldn't need to say this, but the reverse logic is also true. You shouldn't place a bet against NVIDIA or another GPU design company unless you're betting that they will become irrelevant because an AI will take their job away, or they will become irrelevant because a different architecture of neural networks will become dominant and a different kind of chip will be being used for that. Let's talk about whether you should bet on or against AI company themselves. So what you should ask yourself is, do you expect large language models to get much better than they are today? The case against them getting much better is that their performance in training and validation is already extremely high, and there's not a vast amount of new training data being produced anymore because, you know, they've eaten everything that was on the internet before AIs started writing stuff on the internet, and you actually generally don't want to train them on the output of previous generation large language models. If you're going to bet on an AI company, think about, are you betting that they can make more money due to incremental improvements that can be reasonably expected from large language models, or are you betting that they're going to discover something new? As I say, I don't want to comment on whether either of those bets is reasonable, but I just want you to be aware that for yourself of like why you're making the decision you're making. Another group of companies you might consider investing in or betting against is those who are trying to sell AI enhanced products. That, of course, just comes down to whether you think those products will do well in the market in such a way that the business is more successful with them than the other businesses that aren't doing those things AI enabled. Again, I'd encourage you to be appropriately, like, if someone says they're going to use AI to do something and you're already aware that that's something AI can do and they're just productizing it, that you can very reasonably expect to happen, and you can make pretty good predictions about how you're well informed about enough to try and decide how the market's going to react to that product existing. If they say they're going to start using AI to try and do something that AI, to the best of your knowledge, can't currently do, then you need to consider everything we talked about earlier, that there's a possibility that AI can't solve the problem that they're asking it to solve. And in that case, does your bet still make sense? And the final category that's, I think, relatively interesting is companies such as Amazon with their AWS division, Microsoft's Azure division, and so forth, that have bought up lots of GPUs in order to sell the service of training AI models on those GPUs to other businesses. And again, to assess whether you think those are going to succeed, you should think about, do you think other people are going to trust those companies with the internal data that they would need to expose for model training? Do you think, given the difficulties of training AI models that we've talked about, that businesses are going to go for that? Do you think that the architecture is going to remain GPU based? There is a risk that another architecture comes along and all of those GPU investments end up being worthless, but you have to price that for yourself. I'm not going to tell you what you should do, because it depends on your assessment of the relative likelihood of all of those things, and it depends on your risk appetite. Final question that I'm intending to answer in this, well, it's not a question. This one is just a rant for me. Back when I was a student taking AI classes, and again while doing background research for this, I run into assertions that I don't believe are substantiated adequately. It's said that the output of real neurons in biological organisms is either on or off, and that the graduated outputs that we're using in artificial neural networks, so we treat the output as a floating point number, they're significantly different to biological reality. I don't agree with the first part of that statement, and therefore I don't agree with the rest of it. And I have a couple of reasons for thinking that. So the first is, if you build an artificial neural network and you force the output of each neuron to only be 0 or 1, the result is not able to be trained to do anything useful. It just doesn't really work. And so if we can't, in simulation, get something to work when we constrain the neurons' outputs to just being on or off, we should be, I think, appropriately skeptical about the assertion that in nature neurons' output is either on or off. The other reason is subjectively, if I cause certain neurons to fire by poking something into my hand and keep that pressure there, subjectively it feels, I find that I'm able to think about it differently, and I get different sensations over the time of maintaining the same impulse. And that subjective experiment suggests to me, at least, that there's a temporal element to how biological neurons work, and that is probably important. The way I think it works is that, functionally speaking, we do have levels of output from each neuron. It's just done in a different way. So at any given point in time, yes, you can say that this neuron is either firing right now or it isn't. But I suspect that the input side of the neuron is not just looking for, is there a signal there or not? I think it's effectively measuring a pulse density modulated signal. So if it sees one on switch in the, whatever that time back window looks like, it's probably more appropriate to think of it as an envelope with a fairly complicated shape rather than a straightforward window. But if there's no pulses in there, it's definitely off. If there's a few pulses in there, it's a little bit on. If there's a load of pulses in there, it's very on. My feeling is that pulse density modulation is probably a better model for how biological neurons work, and to treat it as there is some gradation there. Now, what the shape of that response curve is, I can't tell you. What the shape of that look back window envelope is, I can't tell you. But I will say that I think what I've just outlined is a falsifiable hypothesis, and I'm very happy to correct my thinking if it's falsified. Thank you very much for listening. Have a great day.